So yeah, so it's the physics teacher, which is the complement to the American Journal of Physics, by the same American Association of Physics Teachers. It's a little
Hmm.
bit more meant to include kind of high school level
Nice.
stuff, but it's really a lot of the same audience. And anyway, you can see that it's basically a kind of a heuristic motivation for the Hawking temperature that you were asking about in your note.
Nice. Okay. Hmm.
Um, and anyway, so I've got the reference to it in our paper already, but um, I was just pondering the whole. So many things are connected, Logan. You know this, but
Right.
so many things are
Yeah.
connected. I was thinking more and more about so the question that first reviewer asked about the Hawking
Hmm.
temperature. I mean, it's
Hmm.
it's like it's such a perfect illustration of the value of what we're doing because it
Hmm.
opens the door for all these things. I mean, I hadn't thought about that at all, but right. So the I'll go ahead and start with this, if that's okay, since
Okay.
you're
Yeah,
yeah,
totally.
since you asked about it in your notes. So I mean, basically the idea is, right, our formula for the size of a black hole, the radius and mass of a black hole that would
Hmm.
form is really a function of density in the static model, right? It's like
Hmm.
the more dense something is, the smaller size black hole you can form to have that critical
Hmm.
mass because of the high density,
Hmm.
right?
Hmm.
Um, then the next step in the chain that we took was to say, well, if it's a gas of photons, with your lovely
Hmm.
illustration of floating around in the sea of light, if it's a gas of photons, then density is really a stand-in for temperature and density are interchangeable. A
Hmm.
given temperature of black body radiation will have a certain energy density by
Right.
necessity, right?
Hmm.
So the temperature we were using in our calculation correctly is the temperature of the photon gas
Hmm.
out of which the black holes form. What this reviewer pointed out that I think is really a clever thing to think about, and I have not yet plumbed the depths of what this will teach us, but is that once the black hole forms, then it's an object that has a Hawking temperature, as you said,
Hmm.
defined by its surface gravity,
Surface
essentially,
gravity.
right? I
Hmm.
mean, because of the derivation, which this paper kind of gives you a nice motivation for where that comes from. The derivation is essentially that when you try to combine quantum mechanics with relativity in the kind of order of magnitude sense, you can think of it as when you have pair creation in quantum mechanics, but it's
Hmm.
happening around a curve at a curved interface like this, you end up with the pairs potentially being separated from each other. And how
I
strong
see.
that is depends on the surface gravity. So that's why that kappa is in there.
Hmm. Hmm.
And so, the thing that Hawking is famous for is essentially making the clearest argument that that means that black holes have a temperature. They're thermal objects.
Hmm.
And because they're so simple, the only thing that can define their temperature is basically their mass.
Hmm.
So that's where you get that formula. I think I put it in the paper now. That formula that it's basically the Hawking temperature is a bunch of constants, H bar and C and Boltzmann's constant, like you said, KB, but it's basically one over
Hmm.
M, right? Other than fundamental constants, the only physical thing is M.
Hmm.
So temperature is proportional to one over M, which is which is crucial for thermodynamics because it sort of brings black holes into the thermodynamic. There was a big dilemma at one point where people were worried that, well, how can entropy always increase? Because you can always just throw your entropy into a black hole and then it vanishes and the entropy of the
Hmm.
universe decreases. But it turns out that doing that increases the mass of the black hole, which changes the temperature of the black hole and its entropy is
Hmm.
associated. And, so it all sort of fits together. But for our
Hmm.
purposes, the thing that's super interesting, and I haven't done the calculation yet to check the reviewer, but I assume they did it right, that the the Hawking temperature for the black hole that forms from a background sea of photons at some temperature is not anywhere near the temperature of the background sea
Mm,
that it
hmm.
formed. Like, what didn't he say it was like
It
different by
was
a
like,
factor of 10 to the minus 14?
yeah, it was like smaller, right?
Yeah. So the Hawking temperature of the black hole is down by a factor of 10 to the minus 14 from the isothermal temperature of the photon gas that formed the black hole.
Hmm.
So the reason
Hmm.
that's significant is that means that
Hmm.
you have a very hot region
Hmm.
around you and you're very cold. So
Hmm.
you're going to absorb energy from the surrounding region at a very fast
Hmm.
rate, right? You've got one thing
Hmm.
at a gazillion degrees and one at some less than a gazillion degree temperature. And so it's going to absorb energy. And that's interesting historically because one of the things in the early papers about this was a discussion about whether these black holes, when they formed, would accrete energy so fast that by now they'd be huge. And so they can't really exist because we would have seen them. And there's a you don't have to follow all the threads of this, but just to know that this plugs us into this whole history of discussion about, so there's a paper by Novikov and Zeldovich
Hmm.
where they
Hmm.
thought that these couldn't exist because they made an argument that they would accrete really fast. And then Carr and Hawking wrote a paper a few years later that said, well, wait a minute, maybe that argument doesn't hold up. So that just
Hmm.
it plugs people into exactly what we wanted in a simple way, which is that we can just make little references to all these kinds of discussions that you can connect to based on this stuff. So anyway,
That's so cool.
so for now, I have that in our discussion section at the end is like the Hawking temperature thing is like one example
Hmm.
of the sorts of things that you can explore in this framework. But anyway,
Okay. And I mean, so when the primordial black hole forms in the sea of photons,
mhm.
is it just like the formation mechanism of the black hole that also incorporates the decrease in temperature of this object? Because I feel like, it's like a process. So how come this like equilibrium, like equalizing process isn't like continuously happening? When was it possible for the black hole to get so much colder than the surrounding temperature if it was kind of always immersed in the same system?
I know. I think that's a really interesting question, right? It's like a phase transition.
Hmm.
It's like some sort of I mean, I think there's a whole, like, yeah, no, no, you should, well, we have it recorded. So
Cool.
you asked that question perfectly. I mean, I feel like that's a research question,
Hmm.
like how to think
That's
about what
cool.
happened to the temperature. I mean, there are certainly examples of things where that sort of thing happens, right? Where the temperatures, something forms and the temperature of the thing that forms isn't
Right.
representative of the background it formed out of. But I agree that's really strange and interesting.
It's
Um,
isn't it like the fire syringe, I guess?
yeah. Right, right, right. Where you do work and you change the temperature because it seems like, well, it'd be interesting to do an entropy analysis on it, right? Because if the
Uh-huh.
temperature is very different, it seems like that would be a different. But maybe that's why. Maybe it's because the black hole amounts to, I think it really is like a phase transition, like because there's like an
Hmm.
entropy
Hmm.
discrepancy, not discrepancy,
Hmm.
there's an entropy jump, discontinuity,
Right.
where suddenly when you form a black hole, yeah, well, that's fascinating. Anyway, yeah, that's a good question. And I do want to check, you might do this as a fun calculation just to double check to
Hmm.
see that like the temperature, but hmm, I think it probably all fits together because there's no reason, our analysis didn't. incorporate in any way what the temperature of the black hole would be from quantum mechanical sort of considerations. So it's really not surprising that those temperatures are totally different
Hmm.
things. Yeah. Yeah. Anyway. Um, so then the other thing, so really good job on the template of um, the letter. I think that's
Yeah.
great. We'll just use that. Yeah, we'll just
And
use that.
I can, for the first, like, I mean, I kind of went backwards. I did the third reviewer first, and then the second reviewer, and then the first reviewer.
Okay.
And when I got to the first reviewer, like, I mean, all the other ones, I just like copied and pasted their exact comment, and so that we had like all the information there and available.
Yep.
But then when I got to the first one, there was so much math in it that I was like, and I mean, I at first like I have a commented out section of the comment that I was like working through it and I was actually putting in like all of the math that
Oh, I see
this
that. Yeah,
person
yeah,
was
yeah.
doing. And then I was like, this is taking up way too much time.
Yeah, 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 yeah. I see.
Because I was like transcribing it from the like I copied and pasted her response or their response this into the document or into the overleaf and
Yes,
then was
yes, yes.
slowly like fixing the math.
Slowly mathematized it. Well, I don't know if you saw this morning, I wrote in the Hawking temperature in there because that was a little bit of a beast to figure out how to typeset.
Oh yeah.
So that's in there.
I've said all that stuff.
Yeah, yeah, okay. Yeah, no, that's totally fine. And I'm not even sure that will end up needing to put all of their detailed comments in because we can just, mostly they were agreeing with us and we're gonna we're gonna include most of what they said in the paper. So I'll figure that
Sure.
out when I get to it.
Because
But yeah,
I can
this is and
totally
I
go
also
in and
sorry.
I was just gonna say I can totally like go in and finish all the math. Like it's not hard. It's just
Yeah,
it was taking up a lot of time and I was like, I'd
yeah,
rather
yeah,
not do
yeah.
that right now.
No, that's good. That's good. And I also commented out just so I don't forget. They this is still part of the anonymous review, so they don't want our names
Hmm.
on the document. So
Right. And
yeah.
I was thinking also like to comment out Logan thoughts and Todd thoughts
Hmm.
when we turn it in. I just wanted to have that
Yep.
there for
Yep.
us to like talk about and
Yes,
yeah.
absolutely. We'll save this document and then, you know, have it as its own archived version from all of
Yeah.
our stuff.
Nice.
And then we'll just merge, Logan thoughts and Todd's thoughts will just become author response,
Nice.
right?
Cool. Yeah.
In fact, maybe I'll just write that in so I don't forget. Let's do this. Yep. Um, so I've spent a lot of time on I feel like I just can't I think I told you by text. I can't completely wrap my mind around how useful the reviewer feedback was for like
Hmm.
I can see from what you're thinking about too. I think it's probably the same thing, but I think so. So if you don't mind, I'm going to try. I think I have the narrative now that will
Hmm.
that will satisfy the reviewers and that will do actually what we originally wanted to do, but we didn't quite know how to do it. Um,
Yeah.
which is that, and I'm gonna. So those 2 pages that I sent you
Hmm.
are a new paper that I hadn't looked at before, and I started looking at because I was trying to understand what the reviewers were saying.
Hmm.
Um, and I think it's the key to all of
Yeah,
this.
it already touched on a few questions that I had written in my Logan thoughts
Yeah, okay, good. And
on
and you can see all of my scribbles. Like
Yeah. Uh-huh.
trying to translate because it's so interesting because they do everything order of magnitude,
Mm-hmm.
and I have to translate it back into like, like, wait a minute. Gravitational
Where did this
potential
come
energy
from?
is just minus mu squared r to the fifth. Where did that come from? And then you realize, oh, well, it's mu is density, so mass is mu r cubed.
Mm-hmm.
So m squared, which is, gravitational potential energy is gmm over r.
Mm-hmm.
So m squared is just mu squared r to the sixth, right?
Uh-huh.
And
Yeah.
then 1 over r from the gravitational potential energy part gives you mu squared r to the sixth over r. And so that gives you mu squared r to the fifth.
Wow.
But I've just never thought of it that way before. So it took me a
Yeah.
while to like, yeah.
Play around with it.
Same way with kinetic energy, right? You look at the kinetic energy formula,
Mm-hmm.
it's mu r cubed r dot squared, and you're like, where the heck did that come from? And
Oh.
then you realize that's just mv squared
Mm-hmm.
because it's mu r cubed is m and r dot is v.
Yeah.
So anyway, and then the Friedman equation, they have reduced to just
Right
r
there.
dot over r squared equals mu, which is true because I mean it's actually really useful. Like we talked about before, I think that's why I like Hawking's papers, is
Mm-hmm.
because he hardly writes anything down. And so
Right.
and so it just makes you think only of the concept, which of
Yeah.
course is what we actually are wanting to do. So
Yeah.
so
Mm-hmm.
so if you well yeah, let me try something. So I think so here's the storyline as I'm imagining it, and I mean I have a bunch of things scribbled in the paper already, but uh, before I try to write it down and let you edit it, I wanted to like try the narrative out on you and make sure that it makes sense
Mm-hmm.
to
Mm-hmm.
someone other than me, right?
Yeah. Yeah.
So, so basically, the starting point is we derived, we took the assumption that there's some region of space-time that is static and has some density,
Mm-hmm.
and we basically found out that under the static assumption, but and yeah, under the static assumption with some finite but big region of space-time that has a density that's uniform, we found what the what the criteria was at that density for how big you have to go to form a black hole, basically, and what the
Mm-hmm.
mass of that black
Mm-hmm.
hole would be that forms under those
Yeah.
conditions, right? So we calculated
Mm-hmm.
that for the static case.
Mm-hmm.
So I think basically our paper can stay just as it is all the way up through that first few sections.
Mm-hmm.
And then we confront the fact that, well, this was nice and it gave us some intuition about what's going on, but there are internal inconsistencies built into our whole argument, and that's okay. We did that on purpose.
Mm-hmm.
But
Yeah.
but the inconsistency boils down to the fact that in the real expanding universe, not only does density, like, high density not automatically make a black hole, but the Friedman equation actually says that the more dense it is, the faster it's expanding. And so the
Mm-hmm.
harder it'll be to collapse,
Mm-hmm.
right? So
Yeah.
we make that link that the Friedman equation actually, really kind of undermines on the surface, undermines everything that we just did for applying it to the real universe, because the whole idea is that you can't have a high density universe that is static. Like it's built into the Einstein equations that if you have a high density universe, it will be expanding or
Yeah.
contracting because those two things are equated to each other essentially, right? And the
Mm-hmm.
density is proportional to r dot over r squared.
Mm-hmm.
So then what's nice about it though is I think, we sort of stopped there and just kind of said that. But it really isn't that hard to apply similar reasoning to just say, okay, well, now let's think about what actually does happen in an expanding case.
Hmm.
And there, rather than it being an energy consideration where we just compare like the escape speed, to find the sword shield radius, we kind of compare the escape speed to the gravitational binding energy. Now,
Hmm.
essentially, we just have another term, which is like a kinetic energy term due to the expansion. And that's
Right.
what Carr and Hawking show nicely how to think
Hmm.
about, right? And then there's one more term, which is significant, especially in the photon case, which is that there's pressure, right? Remember,
Hmm.
we mumbled some things about how
Hmm.
we don't really know if these are actually going to collapse because there's pressure. And so
Hmm.
that's the other thing they add in. So now basically we can really neatly, and we'll spell this out in our paper, we can really neatly have three terms that we're comparing, which is gravitational binding energy is trying to make it collapse.
Hmm. Hmm.
Expansion is trying to make it go apart. And then
Hmm.
pressure is also trying to resist collapse, right? So
Hmm.
there's one attractive force and two repulsive forces, basically.
Yeah. Hmm.
And so those 2 pages I sent you are just them making estimates of what those three quantities are and how they
I see.
scale
Yeah.
with density and stuff, right?
Hmm.
And I mean, I'm not even sure. We may play around with this, but I'm not even sure how much of it we actually need to say. We can mostly just say it in words and then
Hmm.
refer to this, I think.
Hmm.
But we might want to put some of it in. You think about that. But
Yeah.
the basic argument then becomes that okay, we did this calculation for a static case,
Hmm.
doesn't really apply. So let's think about what it would take. Under what circumstances would there be in an expanding universe a region that would cut itself off from the expansion enough so that actually our analysis will apply, which is really cool because we can
Hmm.
just stitch it all together, right? Because what's
Whoa.
going to happen? So here's my understanding of the idea, right? So the whole universe is
Hmm.
with some, let's call it background density,
Hmm.
is expanding at the rate corresponding to the background density. But then the idea is that what if you get an overdensity in some region
Hmm.
that's going to have to be of order the background density because otherwise it's not enough to be very significant. If that makes sense, right? It's, in other words,
I see.
fluctuations are going to be of order the same size as the amount, right? Like,
Hmm.
if
Hmm.
your density is 1,000,000 grams per cubic centimeter or something, a fluctuation of 1 gram per cubic centimeter isn't going to make any difference. The fluctuation has to be
Hmm.
something of order the
Hmm.
1,000,000 grams, right?
Right on.
Within factors of a half or whatever. So, so you get a region that fluctuates enough, which we're just assuming could happen. We're not, we're not, I mean, that's the whole field of, of, people working on this is to figure out what
Right.
those could be. We're just saying, let's just imagine that it happens. And we know that it happens at least at some level because that's how galaxies form. Like there have to be density and,
Hmm.
uh,
Like
we didn't,
seedings.
right. There have to be fluctuations or we wouldn't have ever even gotten galaxies to form, right?
Hmm.
Um, So then remember when we had that discussion where we had the aha moment where we realized, oh, wait a minute, in the region where this is overdense and going to collapse, it's not flat. Okay, the
Hmm.
curvature is not zero.
Right.
And so that's where in that region, basically what's happening is you have a closed little mini universe.
Hmm.
And a lot of the papers throw around the term maximal expansion, and I never quite understood what that meant before or why they
Hmm.
cared so much about that. And I think I finally understand it. It's because the maximum expansion of that overdense region is going to be when it turns around and starts recollapsing.
I see.
And so that means that at that turnaround point, guess what R dot is?
Negative.
Well, it's going to become negative. You're right. It's going
Hmm.
from positive to negative, so it's zero.
Hmm. Oh,
And guess what r dot equals zero means in words? That's static,
wow.
right? Momentarily, you have basically a sort
Yeah,
of like a static region.
yeah.
And so then of that region, you can apply our criteria to say, well, at that density in that region, will it form a black hole? It's almost like the expansion criteria, the Carr and Hawking sort of thing about comparing the kinetic energies is it's almost like we've got not almost we do have two criteria going on. One is just to see in the expansion, no, not worried about whether it's a black hole or not. Just
Hmm.
just seeing within the expansion, is it gonna cut itself off from the expansion and sort of have a region that closes back?
Hmm.
So that's what their analysis does. But then applied to that analysis, we can then ask of that region, does it satisfy our criteria that we set up of will
Hmm.
it form a black hole,
Hmm.
right? Because now it satisfies exactly the conditions we wanted, which is it's a flat universe outside,
Hmm.
also expanding, but that doesn't really matter. It's flat. And inside, it's static. And so we can just ask, is that enough mass for that scale to form a black hole?
Hmm.
And
So
then
if I'm understanding this like correctly, it's like the universe is expanding, and then there's a point where the balance between the like gravitational like attracting energy, the pressure energy, and the kinetic energy of expansion are in a way like equal to each other, so that there's a region in space-time that kind of gets cut off, and like we can kind of imagine, like I don't know, watching like on a TV this happening, and then like once those values become equal to each other, the R dot becomes zero, and we can like press pause and then apply what we have done previously
right,
to the paused TV screen.
exactly, exactly.
Okay.
Yep.
Okay, cool.
And I mean, and in fact, I mean, I guess the recollapse, if anything, is going to help at this point because it'll,
Hmm.
it's like you said, it's going to go negative after that. Um, and of course, there's huge amounts of details in there that my brain cannot track right now. Like
Hmm.
I'm
Hmm.
throwing away vast amounts of information in order to have a
Uh-huh.
storyline that I can follow. But I think, that's the point of our paper, right?
Hmm.
Is to not lose the thread of intuition. And so we're
Hmm.
we're playing the role of filtering through. Like over the last weekend, I read so many of these papers on people calculating what the mass spectrum of primordial black holes would be under a bunch of different
Hmm.
circumstances and
Hmm.
stuff. And
Hmm.
and there's so many different assumptions and so many, I mean, and they all get roughly that um, the fluctuations have to be um, of order the actual density at the time. And so, for our purposes, the details don't matter too much, but I think if we can really give just a story that makes sense about how this could actually happen, we'd be doing a great service, right? I mean, I think
Hmm.
because then you can connect to all these other papers and at least have some baseline of knowing
Yeah.
what's actually going on. So anyway, I was just very excited that we don't actually have to. We're basically just finding a situation where our analysis applies,
Hmm.
which is kind of cool. And then I
Yeah.
think I think that explains why. Remember how we were wondering about the coincidence of why do we get the same answer?
Hmm.
Um, the one piece I don't understand yet is why it's the horizon. Like like it works out that the mass of a primordial black hole that happens at a certain time, that forms at a certain time, is roughly the mass that's enclosed in the horizon at that time, which is the
Hmm.
how far something could have gotten since the beginning of the universe.
Hmm.
I don't understand that yet.
Like
I,
the horizon, as in like the observable use or observable universe,
yes.
like horizon. Okay.
Yes. I mean, I technically C over H.
Okay.
So C
H
C
is in
over
Hubble
C
constant.
as in Hubble constant. C
Okay.
over the quantity A dot over A.
Okay.
And on the second page, Carr and Hawking make a sort of an argument about, like, so they say, sort of, oh, two-thirds of the way down on the second page, they say, thus R is proportional to T, which shows that for the P equals one-third U case, which is the photon case, the
Hmm.
size of the region at the moment of recollapse must be of order that of the particle horizon, the distance light could have traveled since the beginning of the universe. And I follow their math, so I think it's true, but I don't have an intuition about it yet. And we might, I mean, I guess our result is what it is. So it's gonna, like the one we calculated is what it is. And so we should be able to show that it's equal to the particle horizon roughly, I
And
think.
yeah, our particle horizon is the sea of photon horizon, right?
Yes.
Okay.
Yeah. Right. Yeah, I don't know what they call it particle horizon, but it just means C over the Hubble parameter at the time.
Okay.
Just how far something could have gotten. Yeah. Mm. So anyway, and it somehow it has to do with the fact that, yeah, I mean, our radius, I mean, I guess that's all it is, right? Our Yeah, it really is that simple. Okay, that's funny. Okay, so
Mhm.
all right, so let's see if I can make this make sense in a so our answer, if you look at our equation 4, we got our black hole equals basically,
1.27 times 10.
yeah, but I'm looking at the constants and stuff still, like not the numerical. But
Oh,
it's
oh
right,
yeah.
so it's basically C over the square root of rho,
Hmm.
right?
Hmm.
But but R dot over R, I'm sort of being interchangeable about A and R because people use it
Hmm.
differently. But so R dot over R in a flat universe is proportional to rho. Sorry, R dot over R squared is proportional to rho, which means that, and that's H squared. So
Hmm.
H squared is proportional to rho, right?
Hmm.
So that means H is proportional to rho to the 1/2. So C, yeah, I think this is how we can do it. So anyway, so C over H, which is by definition the particle horizon,
Hmm.
that is what we calculated in equation 4,
Yeah. Okay.
right? Because
Yeah.
it's some constants, and then, I mean, not that G is insignificant, but I also left it out of the Friedman equation, right? It's in the Friedman
Hmm.
equation too. So I've been reading too many Hawking papers. Am I being too sloppy? Does that
Yeah.
make sense?
No.
I mean,
Yeah,
basically, I'm ignoring everything except C and rho
yeah.
to see what's
Because
going
it's like
on.
because the in I mean in the paper it was saying on order of,
Right.
so it's
Exactly.
still on the order of it if we get rid of those constants.
Right. So basically, maybe a really simple way to say it is that the radius, the black hole radius that we calculated, scales as rho to the minus one half, right?
Uh-huh. Yeah.
And the horizon size in the universe also scales as rho to the minus one half.
Hmm.
And so that's the sense in which they're saying that the horizon, the black hole scale is the horizon scale. And I suppose, I don't want to speculate. I mean, there's,
Well, like so this is saying that the radius of the black hole is the same size as the observable universe, right?
at that time,
At that
correct,
time. So like the observable universe itself at that time just is a black hole.
correct, correct.
That's wait,
If if it's over dense enough to cut itself off from the rest of the expansion.
right. So if we're talking about the early universe having a bunch of asteroid mass primordial black holes,
Hmm.
how could a bunch of asteroid mass primordial black holes emerge if as each second went by the universe was expanding, but inside the Hubble horizon was just the black hole? Like, would these like asteroid mass primordial black holes just kind of like eventually, like originally they were all just like one primordial black hole, and then they like broke off into like a bunch of other ones? Or like, I guess, how did we transition from the point of everything inside the observable universe being a black hole to now it's a bunch of there's a bunch of black holes?
Your your thought process is perfect. I love watching your face and watching you think because I went through this same thought thing basically. So let me see. I mean, I'll try to do an economy of concepts here to say. So
Hmm.
the key is that the observable universe is changing.
Hmm.
The observable universe at 1 second after the beginning is a very different thing than the observable universe today
Hmm.
because the horizon is expanding
Hmm.
with time. See what I mean?
Hmm. Yeah.
So, so at, let's say at 1 second, at t equals 1 second, the observable universe was 300,000 kilometers across.
Hmm.
But the universe wasn't, but the observable universe was
I see.
from
Right.
any given observer's point of view.
Yeah.
So if you were in a region 1 second after the beginning, or whatever we're calling that T zero,
Hmm.
extrapolated T zero thing.
Hmm.
If you were in some region, um, 1 second after that beginning, everything that you could possibly know about was within 300,000 kilometers of you.
Hmm.
And what we're saying is that if a black hole for let's make it really specific, if a black hole formed out of the conditions at that 1 second time, we're saying that the black hole would have a Schwarzschild radius of that 300,000 kilometers roughly, and that its mass would be however much mass was included in that observable universe at that density,
Hmm.
right?
hmm
But now go to 100 seconds.
hmm
In fact, let's just, for the sake of argument, let's say for some reason the overdensity fluctuations only happened at 1 second.
hmm
So a bunch of black holes formed at that 1 second time. And
hmm
so everybody who, if we had scattered observers all around the universe, even earlier than 1 second, they would each be caught in their little black hole bubble in the regions where there happened to be an overdensity. So I
hmm
think that okay, good. This is a good question because that's the other tricky part is the idea that these are only happening where there's enough of an overdensity to compensate and overcome the expansion.
hmm
And so that means that this isn't happening like completely everywhere in the universe. It's only happening in places where there were fluctuations. And so there's also space in between where these clumps form, where you could be where you're not in one of these black holes because you're sharing in the expansion, right? It
I
doesn't it
think
doesn't turn around. It doesn't go to zero expansion rate,
hmm
right?
I think what's confusing me is like, so I understand that like there's the universe and then there's the observable universe, which is the point where the speed of light is equal to the expansion of the universe.
Well, it's equal to right, right, okay.
And so if like there was a if like the black hole has the same radius as the observable universe, how could there be over dense pockets within the observable universe? Like if like since what I'm imagining is
Good.
that the black hole is taking up all of that observable universe. So where in this observable universe are these other overdense pockets happening? Or is it like you think of the universe and there's a bunch of observable universes happening because the
Correct.
universe is so big and there isn't one place where the Big Bang happened because the Big Bang happened everywhere in a sense. So
Correct.
there's so okay, so there's just a bunch of observable universes in
Correct.
the universe. I see.
So in
I
other words,
see.
so
Okay.
you've reached an important conclusion, I think, which is that the the scale of these density fluctuations has to be of order the observable universe.
hmm
It can't just be a little tiny fluctuation,
hmm
even tinier than like in other words, to some reasonable approximation, it has to be the case that a density fluctuation sort of enters the horizon scale, right? So
hmm
there has to be an anisotropy that is of order the horizon scale at that time
hmm
in order to be significant enough to make that little pocket form. So if you were some sort of super observer who was not limited by the observable universe at your point, and you could look down on the universe, you would
hmm
see in our little model here, what would be happening is there would be density. So there'd be a background density
hmm
that was uniform on super horizon scale, trans horizon scales, right?
hmm
Where
hmm
it would all be the same on a scale that's much bigger than what the horizon is at that time.
hmm
And then somehow you introduce fluctuations that are roughly, in amplitude are roughly, doubling the density.
hmm
And the length scale over which that density is greater is roughly the horizon scale.
Okay.
Do you know what I mean? So
I think so.
if you were looking at the universe in a density gradient sort of map, you would see density peaks that were about the size of the horizon.
hmm hmm
relative to the background.
hmm
And, so they'd be like little
Interesting.
spots, and the spots would be roughly the size of the horizon, is my picture. And then,
So, sorry, continue.
oh yeah, well, so, and then, it's only the horizon. The tricky part is that it's only the horizon at that moment.
Hmm
As time goes on, the horizon grows in proportion to time.
Right.
So, so now let's say you had a bunch of these that formed all over.
hmm
Now 100 seconds in, an observer who was not in one of these density fluctuations, who was in one of the in-between regions, would now
hmm
look around and see, you know, what, 100 cubed, sorry, of these black holes would be in their observable universe now.
hmm hmm
You know what I mean? I think. I
Yeah.
mean, I'm making this up in response to your question, so it's a good
Yeah.
dial, but does that make sense? Like these things would
Yeah.
form on the horizon scale at the time, but then as time goes by, an observer is now able to see many of them because their horizon has grown,
hmm
while these things have not grown
hmm
because they're cut off by their own collapse, by
Right.
the overdensity that cuts them off,
Right.
and they now form into black holes that then some observer would now see, oh, there's what, a million, 10 to the 2 cubed, 10 to the 6, would see, oh, there's a million primordial black holes now in my
hmm
observable universe. And then, a million seconds later, it's a million cubed primordial black holes. And now
hmm
we're what, 3 times 10 to the however many seconds the stage of the universe is. It's like 10 to the
hmm
18 or something like that, I think. I'm not
I
sure.
think then, like, when you think about like the cosmic microwave background, then, and how the regions are so uniform. Like it kind of goes back to our discussions that we were having about earlier about like what if we were to assume that the early universe was uniform?
Yes.
Ha-
Yes. Well,
If if these density pockets of observable universes, like if there were so many of them, I guess maybe that would imply that each of those observable universes kind of had the same density
hmm
at the times that they formed. And so roughly if those observable universes dominated like dominated over the in-between areas, like on average, the density of that, like I don't know. I'm not imagining necessarily the whole universe,
but
but I'm also not imagining like, the observable universe because it's like this horizon encapsulating a bunch of observable universes.
okay.
If you were to take like the average of that region of observable universes, like you would have those observable universes and then you'd have those like in between regions where someone's like, whoa, there's a bunch of primordial black holes around me. If each of those like observable universes had the same density, like if the mass, I guess, of those primordial black holes were the same, then I guess maybe like on average it would be like the same density, not considering the in-between regions.
Right, right, right. I see what you're getting at. Yes. So it has to be in order for these regions to be over dense, it has to be under dense in some other places.
hmm hmm
So that the average density is whatever we say the background density is. I see your point. Yeah, yeah,
hmm
yeah. Good,
hmm
good insight. You're right. The, you were having these regions that just like just like is true now in galaxies or here on Earth or, in
Hmm.
your apartment, for example, right? Your apartment is a huge anomaly
Hmm.
relative to the background density of the universe right now,
Hmm.
right? And there are other places in the universe that are much lower than the average density of the universe. And all
Hmm.
told, that's what makes the average density what it is.
Hmm.
So yeah, and I guess the other thing before I lose it that's important about your question is that now you're starting to get into the usefulness of having this intuitive thread that you can think in
Hmm.
terms of, which is that now I think you can start to see why at the forefront of the research on this, why one of the big concerns or the big topics is what are some alternative models for inflation or some other thing that could
Hmm.
produce large enough fluctuations to make this happen? Because as you said,
Hmm.
we have a constraint on what the density fluctuations can be at the level of the cosmic microwave background structure. And we know
Hmm.
it's only one part in 10 to the fifth, right?
Hmm.
The fluctuation, delta rho over rho is only 10 to the minus 5
Hmm.
at that scale. And that's not nearly big enough to make these primordial black holes happen. And so if you add one more piece, which is that the standard models for inflation and most other things for structure fluctuations, density fluctuations, is that they should be what's called scale invariant, so
Hmm.
that they're the same delta rho over rho, regardless of what
Hmm.
scale you look at.
Hmm.
Then that rules out any significant primordial black holes because we already have a data point that constrains it at the scale of the cosmic microwave background as being too small. So the only way for this to work is if somehow it's not scale invariant, and so the fluctuations at the smaller scale where these PBHs would have formed can be a lot bigger than what the fluctuations were at the scale that formed the galaxies and that formed the cosmic that we see as the anisotropies in the cosmic microwave background. So we
Like for
actually have
seating purposes.
right, right. I mean,
Okay.
the seeding is just another name for density fluctuations, right?
Hmm. Hmm.
Right.
Yeah.
So so now you can start to see all the constraints that come in. I mean, so like our analysis is really just saying, could this happen given a big enough density fluctuation? And then it's a separate, it's a topic for another paper, for many other
Hmm.
papers, to
Hmm.
ask, could you have the density fluctuations that would be required? This is just sort of
Right.
spelling out the mechanism for how this would happen given the density fluctuations that you needed.
Because we need density fluctuations that are on the order of the Hubble horizon itself
Yes. And
in
and
order to
and the
form
amount,
primordial black
right,
holes.
right. And the amount of density fluctuation needs to be of order the amount of mass, or the amount of energy that is in a Hubble volume at
Wow,
that time, right?
that's a lot.
And that's pretty big, right?
So then the time on the cosmic calendar that asteroid mass primordial black holes resided, the Hubble horizons in the
Uh-huh.
universe were the size of hydrogen
Very
atoms,
good.
and the mass inside were of asteroid mass.
Correct.
That's
Right.
wow.
So yeah, so for example, if you were going to form, I mean, it doesn't make a whole lot of sense to call it a primordial black hole at this point, but you can extend your reasoning to say if you were going to form a primordial black hole now, at this time, what would be its Schwarzschild radius and how much mass would it have? You don't have to give numbers, just give a
Yeah,
description of it.
that's interesting. Because I guess because is it because the Hubble horizon is so much bigger
Hmm?
that we're able to encapsulate a lot more mass,
Mhm.
so they would be more massive
Mhm.
and have a larger radius.
Mhm.
Okay, okay. I
Right?
guess that
So,
answers my question
right.
then that I wrote down in my Logan thoughts on
Good.
the other.
Well,
Huh.
now you can, I mean, you are illustrating perfectly why I'm so excited about this because you're like our guinea pig for, you know, all of the physics undergraduate slash beginning grad students who can be thinking this way, right? I mean, and I
Mhm,
include myself in that actually too, right? That I mean, now we can just actually, now all these things fall into place, right? So you look at that equation that we derived, which is that the radius of the black hole is, um, 1.27 times 10 to the 13 rho to the minus 1/2 meters. And you put next to that, which is what we're going to do now in this expansion section, you put next to that how the size of the observable universe scales with density, and
mhm,
they scale the same way.
mhm,
So you can basically say you could make that a function. In fact, we probably should do this. I think I now understand what the reviewers were saying in this one part. We could
mhm.
actually rewrite that equation as the radius of a black hole equals some function of time,
Wow.
right?
Yeah.
So that you could answer your question directly. And in that comment about, I think I agree with them that that probably is better than saying, it's at the nucleosynthesis era or whatever.
Hmm.
We can just give a formula for
Hmm.
you because we know how the density of in the radiation dominated era, we know how the density scales with time.
Hmm.
Um, yeah, it must be
Oh yeah,
t to the
I
minus two,
did
right?
that.
I think it's t to the minus
Yeah.
two. So if we know how the black hole size scales with density, then we also know how it scales with time because the density change is just coming from the expansion.
Hmm.
So that means if you put our current density, actually, we don't even need the time part to answer your question. If you look at equation 4 and or 5, just put in the current density um, in what did we use? Probably kilograms per cubic meter or something.
Hmm.
If we put in the current density, which is very, very low, you'll get that the radius of a black hole that would have to form now would be of order the size of today's observable universe.
Wow.
And the mass would be the mass of our entire observable universe of that black hole. And that makes sense, right? Because our analysis is that this is what would happen if you had a fluctuation on that scale.
Hmm.
But we know that we don't have a fluctuation in our region on that scale because otherwise the universe wouldn't be expanding. It would be recollapsing, right?
And we would either that or we would be in the in-between region where we would be surrounded by primordial black holes.
Yeah, which we could be, right? So we just know
Hmm.
we're not in a black hole of that size. No, you're
Yeah.
absolutely right. This process could be continuing, which is a cool thing to point out that that the same thing we're talking about could possibly be happening right now, that there are other regions of the size that we are that have ridiculous fluctuations happening
Hmm.
where from our point of view they are becoming black holes.
Hmm.
And that as this horizon size expands further, eventually we might be able to see those. as objects. But it's the same thing that you're asking about the very early universe could be happening now. It's just that
Hmm.
um, presumably it happened more easily in the early universe
Hmm.
for these fluctuations to cross the horizon scale than they do now. But it exposes the fact that we still need a mechanism for that. Like our paper doesn't intend to cover why that
Yeah,
would happen. It's just it's just giving some insight into the conditions that would have to happen in order to form the black holes, I guess, right?
yeah,
Yeah.
that's interesting.
Isn't that cool?
Yeah.
So yeah.
So I guess um, because like one of the comments, which I think was this, what we were talking about was like there was this really long description in their revision about the importance of incorporating expansion because that's the difference between the mass scales of primordial black holes and the mass scales of astrophysical black holes.
Right.
So, like for our paper, like we talk about primordial black holes as a dark matter solution before what about expansion?
Right.
And I think like is that well no never mind. Never mind. I think like even though I guess where my brain was like beeping, whatever that means, um, was that like primordial black holes were conceptualized because we knew that the universe was expanding. So there was one point in the early universe where it was the radius was a lot smaller, like of our observable universes, and there was a lot more mass. Like that's where the idea of a primordial black hole arose. So I was thinking, would it be fair to even talk about primordial black holes before incorporating expansion, but in the spirit of our intuition and having this um,
I see.
little
Yeah.
model to play around with? I think it is still fruitful to introduce primordial black holes with this static model,
E-
but I think
e-
it is important to then emphasize that like the definition of a primordial black hole arose because of expansion. And now
Right,
we
right,
have this cool static model that can be simulated because like if we consider the point at which r dot is zero, like we have like those static regions now, so we can apply this.
right.
It's just that thinking, I guess just making a comment about thinking of primordial black holes in this static case isn't necessarily like it's beneficial, but I feel like the essence to get at the essence of what a primordial black hole is, it's important. Like a huge part of it is that expansion part.
Yeah, I mean, the reason they're called primordial is because they happened in the early universe when it was
Hmm.
dense.
Hmm.
Right,
Hmm.
right. That's right. Yeah.
Okay.
Yeah,
So
and
yeah, I think we're good.
yeah, and you can see what you think about what I've done so far, but it kind of in that spirit of what you're saying, I've I've changed the title for one thing, right? So
Hmm.
the title just says primordial black hole formation in simplified toy models. Doesn't say
Hmm.
static anymore.
Hmm.
Um, and
Oh
then
yeah, that makes sense.
yeah, and then in the introduction, so if you look at the last paragraph of the introduction, basically,
Hmm.
and I agree with you. I think it might be good. You can maybe think about how you would want to word that. Um, we could just in that first couple of sentences of the definition of primordial black holes, we could say,
Hmm.
you know. I mean, it's in the references we give, but we could say something about these would be black holes that would have formed in the early dense universe. That's what that
Hmm.
means. We might say that
Hmm.
explicitly, maybe if you
Yeah.
but then the last paragraph of the introduction, I have now changed to give some of the context that I think you're talking about.
Hmm.
So now it says to illustrate the possibilities, we begin by working with a static model. The static model is unrealistic, but very useful for building intuition. We will then
Hmm.
extend the reasoning to connect the insights gained from the static case to the more realistic case of an expanding universe. This will highlight an important contrast with more familiar stellar collapse black holes whose masses are tied to the stellar mass. Instead, primordial black hole masses are tied to their time of formation in the early universe.
Yeah.
Is
Okay.
that,
Yeah.
that's the
Yeah.
sort of thing you're getting at, right? Is that we need to
Hmm.
frame
Hmm.
that early on. So I'm not sure. I haven't
Hmm.
I haven't wordsmithed it at all yet. I just sort of slapped some things in there,
Hmm.
but I think you're totally right that. So I really like the flow of how this can go now, right? Is that we sort of
Hmm.
it feels more useful than it did in its original version because now there's a clear connection to the
Hmm.
real expanding case. But I was scared of that because I thought it meant we were going to have to redo all of our calculations. But
Right.
now I realize, well, actually, we just have to add some embedding of our calculation to like stitch the stitching is the best word I could come up with. Like we're almost
Hmm.
stitching what we did onto some reasoning about what happens in the expansion. And I think that's
I
ideal
think,
for this audience because then they can make connections and
yeah,
stuff.
I think this is like really cool because like I'd never thought like I thought like this, the main motivation for this paper to me was that it was just a like smaller stepping stone one could take to be able to actually understand um the workings of like the early universe and such. And I guess just the origins and general ideas of how the universe works. And now we've created something like I guess well, there's a lot of ideas going in my brain right now. I'm trying to figure out
Yeah,
which
go
ones I
ahead.
want to say. Like the Bohr model of an atom.
Uh-huh.
That's what we did. But
Yes.
for the universe, like
Right.
for when R dot is zero,
Right.
we've created like a Bohr model of an atom, but for the
For
universe.
Yeah, okay. Okay.
And another thing, and I still want to talk to you about this book because we keep saying that we're going to talk about it. But like with the Sparks of Genius book,
Uh-huh.
one of the sections is on abstraction.
Okay.
And I didn't really know exactly what abstraction was. It was just kind of like a blurry topic in my brain. But now like what abstraction is having this sea of complicatedness and being able to communicate the essence of the complicatedness or be able to create a simple structure in which, like, if you were to imagine like a present, like the present itself is simple. It's just like this simple box with like a bow on it. But then, like, the structure of this present, like, is simple, but encapsulates the complicated mess that it originally was.
Yeah.
And so what we're like we are abstracting. We are trying to find the simple essence of the universe by discarding a bunch of complicated details
Hmm.
to get at the essence of the universe.
Uh-huh.
So like our we this process is abstracting.
Yes, this is exactly abstracting. And that's what that's what our building our intuition and all that is. Yeah, and I mean, just to emphasize what you said, I mean, this is true for me too, that like until this week, I did not understand primordial black hole formation, like in the
Yeah.
sense of, like I don't know how to say it exactly, but now I can actually I could ex well, like I just hopefully sort of did talking to you. Now I feel like we can explain to someone a storyline about
hmm
about what primordial black holes are, how they could have formed, under what circumstances they could have formed, why there are these formulas for why they form in different masses at different times in the history of the universe, what would be needed to create the conditions where enough of them actually could have formed, all that stuff.
hmm
Now I feel like I have well, just like we say in the paper, right? I mean, now I have an intuitive thread that I can follow through it. Whereas before, you know, I just had
Yeah.
stacks and stacks of papers where people say, oh, well, if we make these approximations, then we get that delta rho over rho is equal to this, and you know, here's a new analytical formula for the amplitude of density perturbations at the threshold of primordial black hole formation in the universe dominated by a perfect fluid with the equation of state P equals W rho C squared. Just all the I could I could say
All the
all the things,
formulas.
but I had no mental picture
hmm
of, like what you wrote on the board about I had no place to anchor like
hmm
why I should believe that these particular things should happen as described in the
hmm
equations. Whereas now I can match it up and say,
hmm
oh, they're just comparing energy from gravitational potential energy to kinetic energy from an expanding universe and
hmm
pressure energy from
hmm
photon gas not wanting to be compressed. They're just comparing those and seeing whether they could come together. And then if it does collapse and make sort of a staticky region, then the normal Schwarzschild type criterion applies, and we can see whether that region would form a black hole. And then, then
hmm
I can hang all the details on that story that I
Yeah.
can wrap my mind around.
Yeah. It's like the importance of the foresight that you have when jumping into these articles.
Right.
Because like if you just go into it not having any of this foresight, you're like, how
And,
can you even like,
and yeah,
yeah.
make sense of it. And then, like you've said before, you can't vary anything because all you can do is regurgitate
Mm-hmm.
what someone said because you don't
Mm-hmm.
trust if you change anything, you don't trust that it'll still be true because
Yeah.
you don't really know why it's true or not true. So all you can do is
Mm-hmm.
quote it exactly,
Mm-hmm.
right?
Mm-hmm.
Whereas if you have this story, then you can say, well, yeah, but we could imagine if we change this, how that would change the narrative.
Mm-hmm.
So yeah. Yeah, this is turning out to be, I mean, it was a fun project from the beginning, but this is turning out to be more useful to
Mm-hmm.
us and to the community, I think, than I was imagining.
Yeah.
Like I've literally never seen anyone, I have not seen any paper that expresses all this stuff in the terms that we're doing.
Mm-hmm.
So it's not like we're doing anything brand new, but
Right.
to be able
We're,
to cut
I
through
feel
the
like,
noise. We're cutting through the noise.
yeah, yeah, that's what I was gonna say.
Yeah.
We're cutting we're like instead of creating papers that people regurgitate, we're creating a paper that gives people the foresight to then be able to read the other papers and actually hang the information from the other papers onto the
The narrative.
foresight that they had gained from reading our paper.
Yes. Yeah, that's really good. That's well said. I'm really glad we're recording this.
Me too.
Yeah.
We've said a lot of things that I'm
Yeah.
glad are
Yes.
recorded.
Yeah. Cool. Um, All right. So, and yeah, I mean, and this is such a good illustration of, when I was vaguely saying what I thought this process was going to be like, I didn't dream it would be this good, where it's like
Mm-hmm.
exactly what we said is we got it started, the
Mm-hmm.
reviewers helped,
Mm-hmm.
and then now we're going to tie all the pieces together in a much stronger way that I think will be way more useful to way more people because it'll this I'm hoping what we should write is try to write the paper that you want, advanced undergraduates and beginning grad students, you want advisors to point their students to this, to say
Mm-hmm.
if you want a gateway to the literature on this
Mm-hmm.
topic, read this paper.
Yeah.
Because then you'll be able to know what you're doing when you read all the other papers. And so
Mm-hmm.
I'm imagining this to be, all of the REUs where people are doing cosmology,
Yeah.
people going to CERN or wherever, Stanford or Pacific or wherever to do research experiences on cosmology in the summer. We'd like them, if they're doing something on primordial black holes as dark matter, we'd like them to read this paper to start with.
Mm-hmm.
And that's kind of how we should word it and frame it. So, you can maybe, I mean, it's still pretty rough.
Mm-hmm.
And I've started looking at you did, like I said, you did a great job with framing the um, responses to the reviewers. So, um, good job dividing our tasks. So, so I would say now maybe I'll keep working on polishing the main paper, and
Mm-hmm.
you can start reading through and changing things or just send me comments or what, you can start.
Cool.
It's definitely not polished, so be warned that it's choppy yet, but I think there's enough
I
there to
think,
start reading.
yeah, I think what I want to do next is I want to just like write down the insights that I gained
Yeah,
from this Zoom meeting
good.
and just try and like communicate what I found out to other people
Perfect.
in the same position as me so
Perfect.
that we can incorporate those explanations in hopes that it's resonates well with
Okay.
other people at the same
That sounds
stage
great.
as me.
That sounds great. So if you want, you could either, I mean, you could even start a new overleaf document that's just,
Hmm.
Logan's summary of this conversation. That, and
Hmm.
then we'll have that, then we'll have that you can just cut and paste into the paper as
Hmm. Hmm.
as needed. That sounds perfect.
Okay, cool, cool. I'm definitely gonna need this video though for
Oh yeah,
that.
yeah, yeah. I will
There's a lot
as
of
soon as it comes to me, I'll put it up on. I have one other meeting this afternoon, but sometime this afternoon I will put it up on YouTube.
yeah, no worries. I'm gonna be hanging out with my sister for the rest of the day,
Okay,
so I
okay,
think
okay, good. Um, one other. Do you have time for one more quick comment?
yeah.
So one other thing that I'm thinking about doing, if you have an opinion, or you could even
Hmm.
do it if you'd rather, um, is now that we're sort of building this whole framework of kind of energy-based reasoning, like
Hmm.
Hawking and Carr do, about
Hmm.
even the expanding case of, comparing
Hmm.
kinetic energy and gravitational potential.
Hmm.
Now I think it's definitely useful for us to actually put the Newtonian derivation of the Schwarzschild radius in the paper,
Hmm.
as opposed to
Hmm.
just making a side comment that one can do that. So
Yeah.
I started that in section two. After giving the Schwarzschild radius, I say it's worth noting that
Hmm.
even though this is a general relativistic result, the formula can be motivated using a Newtonian calculation of escape speed. And
Hmm.
I mean, it only takes a couple of lines of equations. So I figured I'd just put that in there because then when we get to the part about the expanding case, we can say, oh, we're just sort of expanding that same style of reasoning.
Hmm.
Like, because it's crazy to me that you don't really need general relativity cosmology even to do the expanding case. I mean, like Hawking and
Hmm.
Carr are just making little twiddle arguments based on kinetic energy and
Hmm.
stuff. They're not really using. I mean, they're using the Friedman equation, but they're not
Kansas.
really using general relativity. So again, I think it's just a good lesson of that heuristic thinking, like you said, right? That sort of
Hmm.
what did you call it? The abstract thinking, like in the book.
Yeah, yeah, abstraction.
Yeah. But I am definitely going to put the Friedman equation in there,
Cool.
and then we'll
Okay.
just point to Ryden to if you want to
Yeah.
know more about where that comes from.
Hmm.
All right. So yeah, so have fun with your sister.
Thank you.
Tell her
Yeah, when
hi,
should we
and then
meet next?
well, your schedule. Well, I don't know. My schedule might get crazy next week. But anyway, so what does
Hmm.
your schedule look like? Let's start with that.
Um, I only have one, two, three like training days scheduled for the escapology.
Okay.
Um, so it's still I don't know what next week is going to look like for me.
Okay. Well, why
Um,
don't we? Sorry, go ahead.
I was just going to say like if next week is really busy for you, like maybe we could meet on like Saturday or Sunday, like before next week, but like far enough away to actually make some more progress.
Let's see. Unfortunately, I have a meeting, like a conference this weekend, so it will be hard to
Whoa.
meet on
Okay,
the
cool.
weekend.
Yeah,
It's
no
here.
worries.
It's the PNACP meeting that has um like Northwest physics stuff. Um, well, why don't we do this? Why don't we will meet sometime in the next week. But
Hmm.
I mean, we've got clear tasks, so let's work on the
Yeah.
tasks that we have to work on, and then when we're ready to meet, let's find it. Then we'll figure out, you know, when we have something, you know what I mean?
Hmm.
When we have
And
something to say, then we'll look and see when are we available at that point.
I guess I can look at this. Did they say May 4th for
May 14th.
uploading?
May
May 14th.
14th.
Okay. Okay. I'm gonna put that in my calendar before that.
Yeah.
Oh, I already did put that in my calendar. Okay. Never
Yeah, May 14th is the due date. It would be nice. I mean, I'm hoping I'm gonna be traveling the week before that
mind. Hmm.
and literally probably back home on the 13th.
Wow.
So, so I mean, and not that I can't do stuff. I don't have my computer, so it's not that I can't
Yeah.
do stuff when I'm on the road, but I think just for our sanity, it might be nice to. I mean, I think we're pretty close.
Yeah, I
So,
agree.
if we could, you know, if we could shoot for 1st of May or something to try to just have it done, just
Yeah.
'cause the faster we get it to them, the faster it's going to be published. So,
Yeah.
um, but I also
Yeah. And
don't
I
want
mean,
to drive ourselves crazy trying to get it done. So,
and I think the relief of getting it done and then going on like a vacation,
yes,
like
right,
for you,
right.
like that's gonna feel really good.
Yeah,
So I
yeah.
I, I would be very down for that. Cool.
Okay. So yeah, let's try. I mean, now that we've run all this by each other now, and you've got once we have everything entered into the paper, now it'll be really easy to make it answer the reviewers' questions because you've got all the questions sort of
Hmm.
entered in there nicely. So, um, let's just spend a few days summarizing your thoughts and me trying to put all this, what we just talked about, into the paper, and then we'll meet again to go over the details and how to word things and stuff. And then, yeah, I mean, we might even be able to, well, we'll see. We might even be able to submit it next week sometime.
Wow,
It'd be
that
awesome.
would be awesome. Yeah.
But it'll be like the last time, right? We'll say that so that we have room to push it back when the
Yeah.
reality, the
Yeah.
reality hits us. You remember how many times I said, "Oh yeah, we can finish this by next week." And
Uh-huh.
then a few
And
months
then
later,
when
we
you
actually did submit it. So
yeah.
that's the way these things work.
Cool.
All right.
All right.
Cool, cool. This is super fun.
Yeah, and this is very good. Very much needed.
Well, I mean, I feel like for all the cosmology I studied, I'm understanding some things that I didn't fully understand before. So I'm just thinking
Mhm.
of you going into your Tübingen program, you know, you're going to have such a good grasp of the intuition to to hang all the equations on when you get in there that
Mhm. Mhm.
I certainly didn't have that when I started grad school, so I don't think many people do. So you'll be in good shape.
Thank you, Todd.
Yeah. Yeah. This is so fun.
Yeah, this is really good.
All right.
All right.
Good for now.
See you soon.
I'll see you soon and have fun with your sister.
Thank you. Thank
All
you.
right.
Have fun at the conference.
Okay, I will. Take care,
Good.
Logan. I'll see you.
Take care. Bye.
Bye.